Thank you. Yeah, so thank you very much. So I will talk about using fiber cables as sensors today. And actually, I will start telling a story. I was previously working for a large telecom operator in Norway, much larger than Tampnet. And I was working with fiber optical communication, and we tried very hard to argue for deploying fiber optics, even in the access network. But it was very hard to get any acceptance for this because it was a kind of cannibalism of the business. But obviously, this opened opportunities for other companies for deploying fiber optics, even into the houses, fiber to the home. And as we can see now in the Nordics, in Sweden, Norway, we see very clearly that it's a high density of fiber optics in the network. All over, it's in the transport, it's in the metro, and it's in the fiber to the home. And that really makes me ask the question, so can this be utilized for fiber sensing? It's a high density network. So how about really utilizing all these fiber cables for sensing? That is very interesting thought, I think. So Tampnet, we are a focused company. We are present in the North Sea and the Gulf of Mexico. Oil and gas customers, we have fiber cables to the oil and gas platforms, offshore wind farms, communicating through mobile base stations that we have on the oil and gas to maritime. And we have our international carrier business, offering links, for example, here from Stockholm to Copenhagen, to London. Low latency. So this is a picture showing some of our cables. The cables are subsea fiber cables, and we say that we have a passive network, meaning that we have passive cables. We have optical amplifiers at the oil and gas installations. And this reminds me about another story, actually. It was a couple of guys digging in the ground in the south of Norway. Well, perhaps they noticed that it was some kind of cabin close by, but they continued digging. And, well, it was a fiber cable there. Or actually, it was several fiber cables. And most of the south of Norway went really offline. And that is the case with the fiber cables. The physical layer, they carry both the mobile network, the internet network, and everything. So breaking fiber cables may be very, very fatal. But if you have redundancy, you may connect through another cable. So as you can see, we have several cables running over. So resiliency, that is really important. Unfortunately, in this case, both cables went out on the same side of this cabin, so it went completely dark. So that was no good. It was not a Tampnet cable. So how about sensing that something is going to happen? Even better than do protection switching is if you can actually predict that something is going to happen. And I think we had this mentioned in the talk from Sai in ADVA, that you can actually do some sensing. And perhaps you can predict that something is going on in your network. So some applications for actually using the fiber itself as a sensor here. I think oil and gas, most of you probably noticed that it was some gas pipes that has been leaking recently, caused by an explosion. If you have a fiber cable on top of this, which you actually normally do, you may use that as a sensor, and you can even sense if someone drops something on top of this pipe. In transport, you can actually see trains moving along a rail track if you have fiber cable close to this rail track. Security, that is sensing, for example, someone tampering with the fiber, someone moving the fiber, patch cables in node rooms, or digging activity in the ground. Or, as I will show, activity in the sea, actually. And seismic, the cables that I showed you from Tampnet, we have cables running out across the oil fields. So, of course, it may also be interest for seismic, for actually checking if how does the seafloor look like, and do we also not only seismic but also actually monitoring for earthquakes. If earthquakes is happening, it's maybe dangerous if you want to store CO2, because that's also activity ongoing now, CO2 capture. So I see two main motivations for actually using this for as a sensor. So protection of the infrastructure, as I talked about, this someone digging or doing something with the fiber cable. But actually it may also enable new business, because you may want to monitor geophysical activity, tsunamis, for example. And also for the railways, if some big stones are dropping onto the railway line, it would be good to know before the train arrives. And this is actually something you can see using fiber as a sensor, if it runs along the railway track. Two main techniques. One is called distributed acoustic sensing. There are several techniques actually, but I will just mention two here. These are perhaps the most known techniques. So the DAS, as we call it, it's based on detecting back reflected light, backscattered, because if you send light into a fiber, a small piece of it comes back. And when it comes back, that depends, it's on how far it has been going into the fiber. So you actually use the time, send pulses or something, and you measure the time before it comes back. So speed of light is essential in this. And then you can actually see where in the fiber, you can see the position of some movement or something. And then we have the state of polarization sensing. Then you detect changes in the light state of polarization at the receiver end. It's not as sensitive as DAS, and there is much more difficult to find any position. But it may still have some benefits, so I will explain why. So this DAS, as I mentioned in Tampnet, we have amplifiers located on oil and gas platforms. So we have quite long fibers going to these platforms, and then perhaps further to UK from Norway. So DAS needs a separate fiber as it's implemented today. And it does currently not go through amplifiers. So there is a limitation on the distance, up to approximately, well, maximum 200 kilometers. More typically, it's 100 kilometers. 100 kilometers. But if we would like to monitor our cable, we can do it from the platform side and from the land side, and we can monitor the whole cable, more or less. So that's a benefit with the passive when it comes to monitoring, actually. So very suitable for DAS, and we are doing trials on this. We use DAS from a company called ASN, Alcatel Submarine Networks. They are specializing on this type of instruments. So very small parts of the launched signal is being reflected, and that is what they are measuring on. Actually, what they measure is strain in the fiber cable. And nanometer length changes is actually observed and monitored. And for having a nanometer length change, you will have that even if the cable is buried on the seafloor. Because you will have some very weak vibrations in the seafloor that causes very small changes in the fiber cable, and that is what they measure actually. So they market their product as a product that can be used for detecting troll activities, and I will actually give an example on this. Anchor drops, dredging, vortex, and also measuring ocean currents, rock slides, and so on. And monitor mammal activities actually quite recently. A paper was published on this where you can hear actually the whales. You can actually hear the whales using the fiber cable as a microphone on the seafloor. You can hear the whales communicating. So that's quite exciting. So we installed a DAS here in Lowestoft on our cable going to an oil platform out here and further to Norway. This is a low latency route that we have. And on that cable, we have been looking for ships and trawler activities and all kinds of stuff. It's experimental work. And this is an example where we actually detect a trawler, so a fishing vessel. And the fishing vessel, it has something called AIS, so it reports its location. And these black dots here, that is the AIS information. So the trawler is going like this. The blue line is our cable. And these lines are so-called safety zone. We would like no fishing activity across our cable because it may hurt our cable. So what we see here is that the trawler is actually crossing, and then it goes up here, and it goes away. But how do we know that it's not trawling, not dragging its equipment over our cable? Well, looking at the data from the DAS, we are actually able to see that this trawler is moving up here along the cable with the trawl down. Well, when it was crossing, we don't see any signature of the trawl. So the trawl itself creates waves, quite strong waves, and we are able to see it like approximately 1 kilometer away from the cable to see the location, to see the speed, and how it approaches the cable. So that actually enables us to be in front of any potential accidents, warning that now you're approaching the cable. So this is currently something that is, this detection is really now working quite well, but plotting it live on a map, coordinated with the AIS information so that you actually can monitor this and continuously and warn, that is ongoing product development by some of our partners. So another example of something that has been monitored, this is NorSAR. They are looking for earthquakes and geophysical activity mainly in Norway. And they used the same data as for this trawler monitoring on the same cable, looking for earthquakes. And they could see earthquakes. They detected an earthquake. It's an example of that. But they also detected something else, something strange. And when they checked what this was, it was an underwater explosion. So they could even locate where it was, and then found the position. And this corresponded to something that was observed from the Belgium Observatory. So that's also quite interesting. You can actually, with subsea fiber cables, see underwater explosions. Perhaps something that may be of interest these days. Okay, so to something that I find extremely interesting. State of polarization sensing. So this is really something that is quite funny for me, because when I was a young student, I had a summer job at this big operator in Norway called Televerket at that time. Similar to Svenske Telegrafverket, I think. So the national telephone company. And they were doing research on coherent detection, which was, this was during the 80s, late 80s. And coherent detection was far from being commercial. And it went away for many years. But coherent detection is exactly what we see now in current systems, high bitrate systems, transport network. And we even start talking about coherent detection in the access network, but that is still research. So the problem with this coherent detection at that time, that was state of polarization may change on the cable going into the detector, and that wasn't really solved. So they had to measure it, and my work was to implement kind of test instrument for measuring it. So then I noticed that, wow, when this started working, this instrument, wow, I can barely touch the cable, and I can see really every movement of the cable with this. And okay, that really has inspired me. And now I have seen that, well, it's a lot of research coming up where that actually use state of polarization sensing. As I mentioned, coherent detection, it relies actually on detecting the state of polarization when it's decoding the information. So in modern transponder interfaces in the transport network, you actually have this information available. If you can extract it or not, that's a different story. That's a different story. And that is challenging. That is challenging to get this information from the system vendors. So I think this is a message that system vendors can take back. Please work having this information available. And that would help a lot for any research and any monitoring activity. And Google, they have actually done a lot of research on this, monitoring earthquakes. This is a very long cable. The benefit of state of polarization sensing is that you can go through repeated amplified systems. And this is a 10,000 kilometer long cable that they have been monitoring. And they have seen earthquake. You can see here time after earthquake origin. You can see this is occurring on the fiber cable. So that is quite successful, and they also think that this can be used for tsunami warnings, because you have these cables, subsea cables all over the earth. So obviously it may be an early warning system if you are able to detect this far away. Subsea earthquake, for example, and detect it. The tsunami, it moves quite slowly, and so do the waves through the earth. It moves quite slowly, while it will move quite fast through the fiber cable, because it moves with the speed of light through the fiber cable. So it can really give you an early warning when it happens. But these challenges with getting the information out of the transponders that inspired me to develop an instrument for this purpose, and also the fact that transponders are for high-end systems. It's not for metro, and for sure not for access right now. So I put together some off-the-shelf components. Low cost was the target, and this is something that makes it clearly different from the DAS, because the DAS it has a cost of the instrument like 1 to 2 million crowns. And is it anyone here that are willing to install this on every cable they have? I don't see any hands, no. But perhaps if you can go much lower than 15,000 crowns, which is kind of off the shelf, just put it together type of components, doing any real product on this would be lower cost, then perhaps it could be realistic to add this to all these fiber cables that we have in the network. So this is a box, and it has a HDMI cable, so you connect it to a TV screen or whatever. Fiber input, it's really a simple device. Ethernet output, so you store the information in the cloud. And simplest way to test this was to actually connect it at home, fiber to the home, coming into my living room. So I took this HDMI cable from the Xbox, connected to the Xbox, connected it to the polarization instrument. My kids wasn't that happy with that solution, but anyway. And I just tapped off 50% of the light from the fiber coming into the house, into the box. So I use actually the signal from my local internet company. So then I have done some trials on this, and also first trying it a little bit out in the house. Here is the cat that is looking at this fiber cable, and actually I put some goodies around the cable, so the cat started moving the cable, and here it strikes the cable, and then it touches the cable more gently here. So you can clearly see that the cable is moved by the cat. It's really no problem with the cats moving fiber cables, but the cat is perhaps more a solution, because there are problems with rats and mouses that are eating fiber cables. So if you can detect that, it would be nice. And I think this is really an example that this is something you can detect, and also much faster movements is possible to detect. Here I use an air gun, so shoot with just the air pressure from an air gun and get some quite fast transients that are fully possible to detect. And it creates only small movements actually on the fiber cable. And then to the field experiment, that is the fiber to the home cable. This cable is not buried in the ground. This cable is an aerial cable coming into the house, like 1 kilometer in air. And normally it's very boring. It's stable. It's very stable actually. So this is disable. It's just a kind of noise spectrum that I see. But then thunderstorm came along, and thunderstorms are more exciting. So they created some movements. And when I look, I don't have any artificial intelligence that has looked into this, not yet. But obviously, this is a field where these type of things can be interesting. But just looking at it with, say, my own intelligence, I can see that there are periods here in the millisecond range. So it's quite slow movements in this pattern. And that may typically corresponds to this cable swaying because of rain and wind that comes with the thunderstorm. Another example here. These are very fast transients, actually. Very short transients. It's a sampling frequency of 44.1 kilohertz here. And the duration of this is more like 60, 70 microseconds. So very short pulses. And it's actually a little bit hard to imagine that these pulses is caused by mechanical vibrations. So what may cause state of polarization changes other than mechanical vibrations? Well, actually, it's said that fiber is immune to electromagnetic interference. It's not completely true, because lightning is creating very strong electromagnetic pulses, and lightning actually impacts state of polarization. So I believe this was during the thunderstorm, so I believe this might be caused by lightning, actually, because that will create a wide bandwidth type of electromagnetic fields. Okay, so to sum up, monitoring. One obvious motivation for using the fiber as a sensor is to reveal any potential threats to the infrastructure, to the subsea fibers in Tampnet, and trawler activity is quite a typical challenge for subsea fibers. We have there is also not a fiber that is within the Tampnet network, but fiber going from Norway and up to Svalbard. And this was broken by some reason, and they have seen that trawlers are going across back and forth, and it's like not once or twice, it's like more than 100 times crossing the cable, perhaps with the fishing gear. So actually monitoring if they are crossing with the fishing gear down or not is useful. In addition, and also digging activity on land-based cables, of course. And if you have cables running on power lines, it may be interesting to also monitor if something is going on there. It's all kinds of things happening. Some are shooting at birds on the power lines, for example. This may hurt the cable. So it's very useful to know something about this. Also, we see potential new business from this, because it's really a way to sense both potential explosions, as recently been a thing, but perhaps more long-term, it's for CO2 storage, you need very stable conditions on the seafloor, avoiding leakage if you pump CO2 down in old oil wells, seismic sensing, earthquake detection, whale sound, and so on. So it's a whole lot of different applications for this, and I think we will see within a close time we will see a few applications emerging, but within a longer time horizon, I expect to see much more of this, actually. Okay, thank you.
So we have a question coming over Menti, please.
Yes. I'll take one that is quite lighthearted first, and that's what's the name of the cat?
The name of the cat is Dante.
Someone wants to know if you asked your optical gear supplier for access to the SOP parameters.
We do. And they say, we don't support it, unfortunately.
Okay.
And then I asked the same vendor, help me putting up alien wavelength so I can use my test instrument. Still, it's difficult.
And then a more serious question related to something you already mentioned, and that's, is there any insight from your perspective what actually happened to the Nord Stream 2 pipeline? Any data from the fiber cables? I don't know who asked this question.
No, no, we don't have any data on it. We don't, because we don't have the cables in that area. So we are not doing any monitoring. But what others are doing, I don't know. Perhaps they know more.
Okay, well, thank you very much. Please join me in thanking Steinar for the presentation. Thank you very much, Steinar.